everyone. And ordinarily, I'd hand over to John right now, but he could not be at this particular meeting. But I'm sure he would note that this is our 15th meeting since we started this with the discussion of COVID almost a year ago. And so we hope that things will keep going even as we all get back to actually being in our labs. The one thing I want to mention before we start is I hope that everyone will make a special effort to attend our Ivan meeting before the ENC, Ivan live from Asilomar, before the ENC on March 28th, Sunday morning, 10 a.m. And if we're hoping to, I think from the brochures, you've seen that we're hoping to make this a fun and casual meeting. And John has come up with a lot of great prizes, and we'll be giving prizes out continually to the registrants and participants during the meeting. And we've got a bunch of good talks. The agenda's gone out, I guess, again today. So take a look, and I hope that you'll be there for that meeting. Before we go on then, let me hand things over to Don and to say something about Q1.
Okay, we invite you to get to know Q1. Thank you very much, Dave. Q1 designs and manufactures complete spectrometers from 400 to 600 megahertz with features for routine use and the research laboratory. Want to upgrade an older system? Q1 can retrofit AS and UltraShield magnets for less than you think with complete upgrades, including automation. Q1 offers NMR instruments with excellent performance at an unbeatable price. Q1's operating environment is Spin Studio J. Spin Studio J has a plug-in based paradigm for extending virtually any capability, either internal or external, to the spectrometer, using Java tools for data acquisition, analysis, and connectivity. It's a multi-language platform with hierarchical data format and exportable to most third-party platforms. We will soon release, or have released, a new NUS plugin based on deep learning algorithm published by Sentman University and exclusively licensed by Q1. This advance uses an iterative process of removing artifacts by a dense convolutional neural network for data consistency to speed data acquisition by a factor of 5 to 10 with improved resolution. For today, we'd like to take a probe survey, and we're glad you're here today. And we'd like to solicit your ideas for probe requirements for polymer research. What's your most demanding probe configuration? 10 millimeter, pulse field gradient, variable temperature, and a range. Send us a message either in the chat or during today's presentation via email to info@q1americas.com with the subject of polymer to share your configuration. We will select a name from the respondents to win a beautiful Q1 periodic table cutting board. Thank you very much.
Okay, thank you, Don. Let me turn things over to Krish, who will talk about upcoming workshops.
Thanks, Dave. I just wanted to take a few minutes to introduce what are the topics coming down the pike. In addition to the ENC Ivan live for Asilomar on Sunday, we have a series coming down the pike next month. April 8th would be a topic of my favor, that is craft. I will be leading a panel discussion on craft and with Dave Russell and Gennady Kirish from Genentech and Andrea Seffler, NMR consultant, to talk about applications focused craft technique. Then following that, later in April, Frank Delaglio will be talking about second innings of NUS and the principal component analysis and tools related to those. In May, June, July, we have QNMR by Jose Napolitano, PureShift by Matthias Nielsen, Darcy by Brian Antlek, and then we do have 2 or 3 more coming down the pike, but we have a pretty good pack of talks coming up. Watch your email, and you will be able to attend any of these. Thank you, and I will pass it back to Dave to continue this.
Okay, well, thank you, Krish. Also, all of those, the schedule for all of those meetings are on the Ivan website and at ivanmr.com. And so with that, let me hand things over to Bob, and let's get started with the workshop.
Okay, thank you very much, Dave. As I am getting ready to present my screen, I do want to take a few moments to thank the sponsors of the Ivan workshop. It's been really wonderful that they've had these workshops going during this pandemic, and I'm really grateful that they've given me an opportunity to host this workshop on Polymer NMR. So polymers are very diverse materials. They can take many different forms. Some can be natural, like polysaccharides or lignin, for example, and many can be manufactured. We can't possibly cover all the different types of polymer materials, but I hope that we can cover a nice little cross section to give a flavor of some of the challenges. My name is Bob Berno. I am the manager of the NMR facility here at McMaster University. And if you don't know where McMaster is, I'll just borrow the Ivan logo here. And so McMaster is right about here on the western tip of Lake Ontario. We're roughly halfway between Toronto and Buffalo, New York. So for our presentations, for our workshop today, we have a number of speakers. First off is Professor Harald Stover, who is here at McMaster University. Harald's research covers many different biomaterial type materials. And his talk today is going to focus on gel-like polymers and some of the challenges their group has faced when studying these, and how they've overcome them and what kind of information you can get from that. Our second speaker is Professor David Bergbreiter from the Texas A&M University. And he's going to be talking about looking for signals of the end groups in your polymer. And if you're very careful with your NMR experiments and you can detect and quantify those end groups, you can determine a considerable amount of important information about your polymer. Then we have Clemens Anklin joining us from Bruker. Clemens is going to be talking about some collaborations that he has had with industrial partners, where they have used elevated temperatures and carbon-13 NMR. And when you very carefully look at your carbon-13 spectra, you can determine information about branching in polyolefins. And then our fourth speaker is Dr. Alan Sentman from SGS Polymer Solutions. Alan has worked with many different industrial clients and studied a broad range of things. And so he's going to give us a little bit of a survey of some of the problems that he has dealt with his clients. Rounding out the panel, joining me are Darcy Burns from the University of Toronto and Ken Knott from Virginia Tech. We will primarily be monitoring the chat and asking some questions from the chat. So after each individual presentation, there will be time for maybe 1 or 2 questions asked from the panel. And then once all 4 of the presentations are done, then we will open it up to the whole group. And at that, I'm not going to take any more time, I'll ask Harald to begin with his presentation.
Thank you, Bob, for the introduction. So I'd like to start by thanking the organizers of the Ivan meeting for giving me a chance to talk. So we use Polymer NMR to solve a number of practical problems that we have in the design and synthesis of our different polymers, polymeric material. The work I'll talk about was mainly done by two graduate students, Sam and Allison, and we'll see pictures of those at the end of the talk. So most of our work starts with the polymerization of two, sometimes three monomers, monomer A, monomer B, into reactive polymers that then combine to form cross-linked hydrogels. And the challenges we have are monomer conversion, but also the functional group chemistry when the polymers cross-link and react further. Some of the applications involve making little microgel particles that are about 10 microns in diameter. And one of the things we target with those is to make synthetic organoids. We come with cells to see if that can enhance cell function for some therapeutic applications in future. Most of what I'll talk about today involves our work in designing and making polymer capsules. These are hydrogel capsules made of cross-linked polymer shells or to house transplantable beta cells. An example is shown here, and the idea is that this could be a biorational new pancreas for type 1 diabetics, where the cells can receive glucose and produce insulin while they are protected from immune rejection by the polymer shell. So it's a medical device, if you like. And polymer chemistry is used to design these and make these, and NMR is critical to figure out what is going on in these systems. There are about 5 or 6 things we'd like to know from NMR. One is copolymer composition, reactivity ratios in the composition. And because we work with functional polymers, I can tell you that we have not worked in one polymer that does not show sometimes desirable, sometimes undesirable reactions and degradation. And finally, we want to do all of that not just in soluble polymers, but also in cross-linking gels. So the problems that we are facing in practical terms are, as you know, when you look at an acrylic or a styrenic polymer, you've got different stereochemistry that can happen along the backbone, isotactic, syndiotactic, alternating, or random tacticity in an atactic system. And that leads to scrambling of the local environment and broader NMR peaks compared to small molecule NMR. And in addition, when you cross-link these polymers, then even though you have linear segments that may be swollen and quite mobile, think of people skipping rope, what you cannot have is end-over-end reorientation on the NMR timescale. And so there is residual anisotropy, usually due to dipolar coupling that we have to deal with. And you'll see that we use magic angle spinning to eliminate that. So the first example I'll talk about is a pair of mutually reactive polymers designed by Alison Stewart. One polymer is functionalized with a diene, the other one with a dienophile. And these are set up a bit like a Velcro system, where when the two polymers come together, they spontaneously cross-link through Diels-Alder coupling. And we can use this to make a quite uniform, monodisperse, swellable hydrogel particles that ultimately can house cells for impulse cell-based therapeutics. The chemistry is a click reaction. And our challenge is we want to measure the rate and the extent of the reaction, because in cross-linkable systems, the reaction will never go to completion. And we also have hydrolytic site reactions that come from anchoring sites. Let me switch to a laser pointer, the anchoring sites, but also the imide itself in the gel. For that, we go back to a technique that we worked on a number of years ago when I was a young postdoc. We realized that if you have lightly cross-linked polystyrene gels, static NMR gives you very broad aromatic aliphatic signals, but a little bit of magic angle spinning of the swollen gel will collapse these patterns. Spinning sidebands move out as you spin, still relatively slowly. And so you can get proton and carbon NMR without any cross polarization, you can get highly resolved solution like spectra. And in chemistries where you have a functional group at the cross-link, this is a dimethylsilane cross-linker, you can even resolve different features of that cross-link at 0 ppm. When we apply that to our current system, the spectra are not quite as clean, but we can follow the disappearance of the two functional groups shown here over time. And I compare a solution NMR with a magic angle spinning NMR, and we can see the appearance of the cross-linking site. We also see other peaks more highly resolved, such as here and down here as well. And so that helps us figure out what is going on inside the gel. Most of the polymer is mobile, but the magic angle spinning adds this end-over-end tumbling that we need on the NMR timescale. The only difficulties are the spin rates are very, very slow for magic angle spinning. We need O-ring-sealed end caps to prevent leakage of the solvent. So we can apply this, and I'm just showing a few sample spectra. The most important point that we learned from this technique is that as the polymer reacts, not only do we have cross-linking that drops our two reagents, the imide reacts faster because it also hydrolyzes in a side reaction that's relevant to our scale. So that allows us to get chemical insight into the formation of these gels. The next question that we have to address is, once we want to implant them, will these actually be immunoprotective or immunoevasive so that the encapsulated cells don't get attacked by the person's immune system? And that brings in work done by Ross, who developed a polycation, a smart polycation, that we can coat onto these primary gel beads that are based on calcium alginate and anionic carbohydrate. We can cross-link that shell to a bag, and that causes a problem because these cationic groups from these ammonium groups here are highly problematic. But we've designed a spontaneous hydrolysis feature into these groups. This ester here hydrolyzes over a couple of days, and that allows removal of a number of these cationic groups. We generate anions. The overall polymer shell now becomes overall neutral in charge, and so these are now immune evasive shells. But the problem is, of course, we need to be able to track this. And at first, we tried to look at the conversion using polymer NMR, but then we realized we're getting a small group that falls off. And as you can imagine, this is a lot easier to track. And so we track formation of small molecules during this hydrolysis in linear polymers. We've done it in gels as well. In addition to the broad peaks of the polymer that disappear, you can see the appearance. F and G are two peaks that come from this ethanolamine. So what we always do is try to simplify and basically not do polymer NMR, if you want it in a sentence. If we have to, we'll do it. Otherwise, we look at small molecules that we can detect. So while this system is working, we realize there are additional challenges. Whenever you make copolymers by copolymerization of different monomers, you should worry about, do they incorporate at the rate that you need? Is there a compositional drift as you consume the monomers? And how do you analyze it? So copolymer NMR is a classic way of doing that, but the peaks are very broad. Here is just one of our cationic charge shifting monomers. It's a relatively simple molecule, but in the polymer, you get broad peaks. And if you were to make a copolymer incorporating another primary amine for cross-linking, might be difficult to see the shedding of the small functional group or the composition of copolymer. But the monomer, of course, has beautifully sharp signals, and in particular, the vinyl groups, which are very small here, but believe me, they are sharp and easy to quantify. So tracking relative consumption of the two vinyls allows us to track the shift in composition of the polymer over time as it's formed. And that is very important because we realize very quickly that these two comonomers don't play with each other. Monomer M1, which is the bigger one, actually is more reactive, gets incorporated preferentially. So as the polymerization continues, polymer formed later is rich in the other monomer. And so we can analyze the data to figure out what's called the reactivity ratios, which is the propensity of monomers to react with another monomer of the same species or to cross-propagate. So it allows us to analyze and ultimately predict the composition of these in these systems. And so the outcome of this one outcome of this one was to say, well, if you look at this little methyl group here, if you get rid of that and go to the corresponding acrylate, this monomer polymerizes faster. And now as we go through the copolymerizations at different ratios of M1 and M2, the composition does not drift. So now polymer formed early and formed late during the 8-hour polymerization has exactly the same composition. And that's reflected in reactivity ratios. If they approach 1 and 1, it means they really want to copolymerize in a purely statistical fashion. So that's a quick introduction into the way we use NMR, usually to get rid of the challenges of polymers and really take advantage of the power of NMR to allow us to quantify in real time conversion, degradation, usually by looking at small molecules that either are consumed or that off the polymer. And magic spinning allows us to do that in the gel state. We don't need CP mass. It would not work in these mobile systems. Magic angle high resolution is perfect for that. So I want to give a shout out to Sam and Allison, shown here, who did most of this work. Some members of the current group that are continuing with that. I really want to thank Bob and Hillary of McMaster NMR facility, without whom none of this would have happened either. And of course, the usual funding agencies. So with that, Bob, I thank you, and I'll hand it back to you.
I might jump in here. So this is Darcy here. Hi, Harald.
Hey, Darcy.
That was a great talk. Thank you. Thank you very much. We have two questions that I got in the chat directed to myself. One is specific and one is broad. So I'll start with the specific one. And it was just repeated in the chat. So Ken mentions that he'd be interested in the hardware requirements for mass of solutions or magic angle spinning spectra of solutions. So he was curious whether the work was done on a solids probe or perhaps an HRMAS/nano probe. What was the hardware setup for these gel experiments?
Thanks, Darcy. Yeah, this work was done in a conventional solids probe, just without cross polarization, using little sapphire spinners, usually 5 millimeter. I think we used 3 millimeter diameter, with just O-ring sealed end caps. And it's a little fiddly, they tend to break. And I usually make sure that I'm the one that breaks them, not my grad students. They appreciate that. There's enough $100.
That's pretty good. I guess the broad question, I'll start with that next. So Jake asked if you might be able to explain the technique of magic angle spinning for somebody who has not encountered that technique before.
There are many people that are better qualified to do that, but I'll give a simple explanation. So in magic angle spinning, the sample container is not a vertical NMR tube. It's at an angle of about 54 degrees to the vertical. And what happens at that point when you spin fast enough, which is about 1 or 2 kilohertz for us, you spin out dipolar couplings. You artificially make the environment isotropic, so solution-like. In solution, small molecules and even linear polymers can tumble so that there is no average contribution from particular neighbors with dipole moments, protons that couple to your proton of interest. Magic angle spinning of a gel provides, see, with swollen gels, Most of the averaging does come from segmental motion of these chains. It's just the end over end is not available on the NMR scale. And so a little bit of magic angle spinning will collapse the broadening due to that. Bob, correct me if I'm wrong. You can do it better and shorter. Or Darcy.
You described it very well. The only thing I will mention is when you described the probe that you used, you were talking about when you were a postdoc. Your students here, we used what's called an HRMAS probe. So it is designed for exactly these kinds of samples. You cannot use it for cross polarization. It can't handle the kind of RF power typical in cross polarization. That said, a conventional 4mm MAS probe would also work. So that's the only point I would make on that. If there are any other questions about that kind of thing, I'd be happy to ask. So. At this point, though, I think in the interest of time, I'll thank Harald, and I think we will now move on to the next speaker. So David Bergbreiter from the Texas A&M University.
First of all, I'd like to thank the organizers for the opportunity to visit Canada. As you know, you don't allow us to come up there now physically, but I guess you do allow us to come up there virtually. So I appreciate the opportunity. What I'm going to talk about is something that's a little bit different. It's really not a polymer project per se, I suppose, but polymers are intimately involved in it and are required. What we do is we use C13 coupled proton NMR spectroscopy to do a variety of trace analysis. One of the things we do is we can use this to determine number average molecular weights for at least some soluble polymers. And I'll give you some examples where it works, and I'll try to give you some examples where it will not work. We've also used this in some occasions to quantify N-group modifications when we don't have a good handle, though the example I'm going to show has a handle we could also use otherwise. And then I'll show how we actually use this in some current research. Not polymer research per se, but we use the polymers as effectively allow us to do trace analysis at part per million levels. So this slide really basically shows almost everything that I'm going to talk about except for the trace analysis, and shows that if you have something like a PEG 2000 that has a methoxy group, you'll see this methoxy group. You'll see this peak right here that's way off scale. That's the PEG group. If you modify this to make an ester on one end and you still have the methoxy on the other, you'll see a new peak that corresponds to the CH2 of the ester. Further upfield, I don't show it on this, you'll also see the CH3 group of the ester. But in addition to that, if you look very carefully at this particular polymer, either at the starting material or the product, you'll see these two peaks that are highlighted with magenta dots. And those represent the C13s that happen to be in this PEG 2000 chain. Now, normally you don't see this. Normally, if I have my students, if I say, what does this PEG 2000 look like? Is it really PEG 2000 or something? They will probably do a GPC, but they could actually do it by NMR using an internal standard. And when they show me this NMR spectrum of this, the PEG without anything else there, it typically looks like this because they keep the PEG group on the vertical scale of the paper. And then you can see this little bitty thing over here, and that's a methoxy. Well, if I ask them for a little bit more detail, or I want to sort of see what that methoxy looks like, they might blow this up. If they do this on a 300 megahertz NMR, it works fine. You can certainly see the methoxy and the PEG peak. But if you go to 500, you see the methoxy, the PEG, and you see this peak here and this peak here. Those are the two things that had that magenta dot on the thing before. If I wanted, I could have also had an internal standard like dichlorobenzene here as well. Now, one of the things you like to do one of the things you have to do with the polymers you make or the polymers you buy is you have to find out the molecular weight. And when I have a methoxy group like this, I can integrate this peak relative to this peak here. Normally, this peak that I've got the arrow on, the laser pointer on, is going to be an area of about 180 if it was really a 45 mer polymer. And this would be 3. And I can integrate 180 to 3 sort of well, but it's still a pretty big number to a small number. If this were 450, that is if the polymer were 10 times larger, this would be 1800 to 3. 1800 to 3, I can't really integrate. That's like measuring the weight of a flea by taking an elephant that has 10 fleas, cleaning it, and then weighing it again. You're going to get lousy numbers. So what we realized was you have this peak right here. This peak, if we say 0.97% C13 natural abundance is really 1%, so we have simple numbers. This peak here, I said, would be 180. This peak would be 3 if it was monofunctionalized. This peak here, or this peak here, would be roughly 0.5% of this peak. That is, this would be 0.9. This would be 0.9. This stuff in here would be 180, and this would be 3. If I add a little bit of an internal standard, I could have a small amount of internal standard that would be an area that would correspond to 1 or 3, and I could actually do that integration also very well. The nice part is that this relative to this is always going to be the same. This is always going to be 0.5% of this. And so even if I made this polymer 10 times larger, I would still be able to see this peak. This would now, instead of being 0.9, would be 9. And I could integrate 9 relative to an internal standard or 9 relative to this, and I'd still know how many repeat units I actually had. We can do this in this particular case. We've done this with internal standards or by integrating the small methyl peak to the main peak of the polymer. And we typically get numbers that are roughly the same. Basically, the polymer is supposed to be 2000 Daltons. We find it's more like about 2150 Daltons or 2200 Daltons. If you then go off and take this polymer and you do the chemistry that I described where you put a functional group on the end, if it was a starting polymer that had an OH and an OH, well, it would be hard to tell how many esters we actually added. When it's got an OH and an ME, well, we can clearly integrate this peak and this peak of the ester. This is the purified polymer. So this peak of the ester, that peak of the OCH3. This is a little bit of water. This is the CH3 of the ester group, this one here. This is the OCH3. And then we still have these satellites. And so we can integrate this relative to the satellite to see how well the functionalization worked. We can actually have an internal standard, integrate it relative to this, or of course to these N groups. And again, we get these same sorts of molecular weights. We see that the polymer that the crude polymer here that's still got some triethylamine and some other junk in it, has a slightly lower molecular weight than the polymer that's purified, but that's expected because the purification involves a fractionation. Now, this chemistry works reasonably well for PEGs. It doesn't work for everything because there are issues. The tacticity issue that was alluded to in the previous slide. If you have a group that's out, in, out, in, out, you're going to get a broad range of peaks. That's going to confuse what the NMR spectrum looks like. I don't have that problem with the, obviously with the PEG. The microstructure matters. Low density polyethylene, one of the later talks might talk about polyolefins. In a sophomore organic class, low density polyethylene is just CH2 taken an infinite number of times. In reality, there's butyl branches every once in a while. There's also even longer branches. And so it's not as clean as just CH2s. You also have issues of viscosity or solubility or aggregation. And in that particular case, I would point out one example. We've done a lot of work with N-isopropyl acrylamide, and we've made copolymers that have isopropyl and tert-butyl. When we try to analyze these, the problem happens in NMR spectroscopy. These materials, because they have a tert-butyl group, they tend to aggregate. They have a so-called lower critical solution temperature. They fall out of solution as you heat them up. And in an NMR tube, they start to aggregate and you start to see just broad spectra. And so even if you could look at this tert-butyl group because the methyls are relatively far away from the place where the tacticity is, that really doesn't work. Now, these polymers here, when I was making up this talk, I think vanillidine chloride, polyisobutylene oxide, even a so-called Celcon, a polyoxymethylene polyethylene oxide copolymer, sometimes called Celcon. It's made by Celanese. I think all these could probably work using this technique. We've just not done that because we don't, other than using saran wrap, we don't use vanillidine chloride. I've never used this particular polyoxybutylene, and this material, I've only talked about it in sophomore organic chemistry and its relevance to plumbing issues. Now, the other thing we do with this, though, is we actually use polymers and modify polymers. We generally don't make them that often, but sometimes we have to. But we use them a lot. And one of the things that we're interested in is doing trace analysis. And in this particular case, if you take something like a dichlorophenol, like this 2,5-dichlorophenol, if you put it in water, it's going to contaminate water at a low concentration. If you take something like a C30 hydrocarbon, this is really just a sort of a low viscosity form of motor oil, and we can make another polymer that's got an imidazole on it. Imidazole is a good base and can coordinate or hydrogen bond to this phenol. And this material in this hydrocarbon phase, the hydrocarbon, of course, isn't soluble in water. It's a C30 hydrocarbon, so it's only soluble at less than a part per billion level. We can take these two, and we can take a water solution that's contaminated with this and add some PEG. In this particular example, I think this was started off as probably only about less than 100 ppm. But sometimes we have contaminants like THF that would be present at much higher concentrations. But if we take this material in water, you can see this material, those peaks show up, and we can integrate these peaks relative to this satellite. We know what the molecular weight of this material is because it actually had an N group. We could calculate it from that or from an internal standard. And so you can actually determine that this started off at a particular concentration, let's say 40 or 50 ppm. Then when you heat it, then when you stir it, and then you let it do a gravity filtration, you can look at the clean aqueous phase. And the clean aqueous phase, all you see is this C13 satellite of the PEG. And this peak is essentially gone. This peak is gone. This peak is gone. In this particular case, this would have been, this was a 1,000 ppm PEG. And so this would have been 5 ppm of the C13 satellite, and the material's gone away to the extent of less than 1 ppm. And this works for a whole variety of substrates. Another example would be BPA, bisphenol A. And again, this is before looking at the satellite. This was a higher concentration of the phenol. But again, after, it's dead flat here. I could have blown this up, but this was the spectrum that I was able to get easily. So this is the way we use this C13 natural abundance, both for determining molecular weights, for looking at the extent to which we actually managed to functionalize a polymer, and then we actually use it for trace analysis, which is perhaps not the most common thing people think of for NMR spectroscopy. I think I've used my 10 minutes, though I don't know precisely when I started. I have to acknowledge the people that did this. This is something we were doing in the group for a long time, actually. But Mary Harald, who was interested in undergraduate education and getting a job at a so-called PUI, was using this to look at contamination in biphasic mixtures of polymers and organic solvents. And then I suggested we do this as a JChem Ed paper, which is where that first figure came from. And then Malinsky and Rosenfeld, Tom and Neil are people that have been doing a lot of the trace analysis chemistry. The work was originally funded by NSF and is currently funded by the Welch Foundation here in Texas. I think I've used my 10 minutes. I'd be happy to answer any questions.
Thanks, David. It's Darcy here. Welcome virtually to Canada. Good to have you along with us. So there is a question and comment in the chat. I'll go with the questions. These come from William Wolf. He has two questions, so I'll go one by one. So the first is, do the differences in the peak heights, I suppose for PEG and that, affect the quality of their integral by hitting the threshold of the analog to digital converter? I might also add, do you have to worry about the nature and vintage of the equipment you're doing these measurements on?
You have to worry about the nature and what?
Vintage of the equipment.
No, we've not had to worry. I mean, obviously this is going to work better on a 500 than on a 300. It's going to work better on if you go down to a 200, it probably won't work very well because the satellites will clearly be on the slope of the large peak. But on the 500, it actually works reasonably well. In terms of what was the first question?
Right. So William wanted to know if the differences in peak heights affect the quality of their integral by hitting the threshold of the ADC.
That's you clearly run into a problem if you talk about whenever you're integrating something that's 200 relative to 2, you're going to get slightly crappy numbers. If it's 2000 to 2, the numbers are just garbage. And the errors in the integration of the errors in integration of the 2000 are obviously bigger than the area of 2. Now, there is one thing that you can do. There is one problem you do have is sometimes if you looked at some of the spectra, if we don't get absolutely flat baselines, what you have to do is you have to go back to the sort of an old-fashioned way of actually integrating areas, which is you blow them up, print them out on Xerox paper, and cut them out and weigh them. That sounds dumb, but it actually works. It can actually be faster than screwing around with something else.
That's fantastic. I love it. I guess William had a second question here that's technical. Can selective pulses be used on the large polymer peak, but not the satellites, to improve the quality of these results?
Maybe, but I don't know. That's a question that's the question I would ask the NMR expert in the department, who is not me.
Fair point. And William
I'd ask you probably more than I ask somebody else.
Well, William's suggesting similar to solvent suppression, but that's fair. That's fair. Bob, are we?
Yeah,
how are we doing?
I think we should move on to our next speaker. So again, thank you, David, for that. So next up will be Clemens Anklin. So Clemens, can you please start your presentation?
Sharing the screen. Well, thank you very much. Thanks for the opportunity to present here. It's always a pleasure to be in this illustrious group with so many names. To see them, it's almost like being at a physical conference, which you might soon be at again. So let me get started on a few points I would like to address in the Polymer NMR. Here we go. So I would like to go over a little bit over sample preparation and solvents which are used in Polymer NMR. But first an introduction, and I can go really quickly here because a lot of that has already been talked about. So NMR can really provide information about the structure of the polymer. Do we have linear, branched, cross-linked? Do we have a copolymer? What is the structure of the copolymer? Alternating, random, block? All these things are fundamentally visible, and it has been brought up, tacticity is something where NMR can be helpful. The primary challenges of Polymer NMR in the liquid state, I'm not looking into heavily cross-linked, which is something more for solid state NMR. We have issues of solubility. Some of these materials are not very soluble. We have viscosity issue. They're gooey, they're thick. We just heard about the dynamic range issue where we deal with very large signal from a backbone of a polymer, and sometimes a lack of chemical shift dispersion. So similar units have similar chemical shifts and are on top of each other. So first, talking about the solvents, many polymers require special solvents because they're not soluble in the standard NMR solvents, or we have to work at higher temperature to be able to look at those polymers, to have them liquid, the viscosity low enough that we actually get narrow lines. And some of the solvents used are common. Chloroform works, but of course you can't go much more than 55, 60 degrees centigrade. With that, you go to other solvents like the tetrachloroethane, which gets you to almost 150 degrees, or things like toluene D8, or also the dichlorobenzene, ortho and para-dichlorobenzene have been used. And the what I would call the scary solvent is deuterated sulfuric acid, which once I heard of a case where a 10 millimeter tube of sulfuric acid at about 130 degrees cracked in the probe. Gives an interesting result. As I mentioned, sample preparation can be tricky, which, by the way, is one of the, aside from sensitivity, is one of the reasons people use 10 millimeter tubes. For polymers, it's just easier to get it into the larger diameter. But if you have something medium viscous and you try to get it all to the bottom or get it bubble free, centrifuges are really helpful. And the hand crank centrifuge is a wonderful tool for almost any NMR spectroscopist, because you can effectively spin the viscous material to the bottom of the tube, or you can spin the solution to the bottom of the tube, and the air bubbles being lighter, they go up. Or if you have a fancy centrifuge like the one on the right, you can put it in there, you tape the tubes down to the hub in the middle, close the lid and spin it for maybe 30 seconds to a minute at less than 1,000 RPM, and it'll be fine. The next aspects are probe, and we heard Don earlier asking about input about the probes. We know that key components for polymer NMR is variable temperature. So you want to go up to typically 120, 130 degrees. That's where a lot of the solvents are close to the boiling points. There are also dedicated high temperature probes, which can go up to 400 degrees C's, where you can work with polymer melts. And that is definitely an interesting approach for these types of material. Due to the required sensitivity, you often work with large volume probes, because if you're looking at end groups or rare features in your polymer, you're not going to have a lot of that in your material. So you bring the overall material up to get the sensitivity on the small peaks you're looking at. One of the major issues in carbon-13 NMR of polymers is proton decoupling. Because what happens is that most of the composite pulse decoupling schemes will give you a certain amount of sidebands. And these decoupler sidebands appear at positions which are related to the pulse width of the decoupling frequency and also the decoupling cycle. So whether you use a volt 16 or a volt 65 or whatever sequence you use, you get a different pattern of those decoupler sidebands. And there has a lot of development has gone into decoupling sequence to minimize decoupler sidebands. So one way is just getting fancier sequences. So if you look here, we start on the left with a simple volt 16. That gives us a sideband pattern. By the way, this is carbon-13 labeled methanol. So I get a huge peak. So I see those small peaks. We're at about a factor of 10 below what would be a satellite height if you have more than one carbon in there. You go to a volt 17, you can see you change the pattern. You go to a volt 64, you again change the pattern, and the volt 65 gives you one of the cleanest sequences without going to fancier schemes. Of course, there are adiabatic sequences or decoupler sequences which use adiabatic pulses. You can put them in an MLEF supercycle or a P5M4, P9M4. There are lots of these cycles around, which again will give different patterns in terms of bandwidth and the sideband patterns. Now, these sidebands actually do exhibit a phase behavior that is determined by where in the sequence you start the decoupling. So one of the solutions which have been proposed is to systematically vary the start of the sequence. One way to do that is to slide it towards before the pulse and just repeat that. So with every scan, you move it a little bit to the left in this diagram, and you accumulate all of these. If you actually look at what happens in an experiment where I do one transient per row, and on each row, I move my decoupler sequence a little bit, you can see all these sidebands here, they change phase, but they change it in different frequencies. And if you do it often enough, you can actually cancel out the decoupler sidebands. So these are, the other possible approach is to shift the decoupling sequence to the right, but you can't have a gap. So what you do then is you do a series of typically higher power pulses to get a little bit of better behavior in there. And with that, you can now reach excellent performances. So again, if we start with our volt 16 here, which gives us this decoupler sideband pattern, we go to a bilevel volt 16, we can see that we can eliminate the lot. But if we take the volt 65 and do a bilevel volt 65, where we use this stepping of the decoupler sequence into the acquisition, we can see if we have our 0.05% level here, we get this much lower. So these two peaks, or these three peaks here, are actually real impurities in my sample. Absolutely hopeless to see them here. Here you have a glimpse of where they are, but in this spectrum, it becomes very clean. So if I blow this up, I'm really at the plus minus 50 parts per million level, and I can now see, I see my methanol signal. I actually see the natural abundance monodeuterium isotopolog, and I see the impurities in here, and these are well below. I think these little guys here are in the order of about 10,000 to 1 and even lower than that. And I would like to finish off with just a recent collaboration I had with some colleagues or friends at Dow. We published this at the beginning of the year in Macromolecules. Another signal which can affect the detection of low-level peaks you want to look at, here a branch point in a linear low-density polyethylene. We see that the peak of interest is actually here overlapped with the carbon satellite. And the question was how to get rid of this. And of course, carbon decoupling carbon spectra is a homodecoupling mode, so this is not necessarily the best way to do it. So I thought, why not take, so if I look here at the model compound N-butyl cyclohexane, I see my signals and I see the carbon satellite. So these are the molecules which contain two neighboring carbon 13s. It's actually nice here. These are close to each other. They are neighboring carbons also in the molecule. So I have an AB system in my carbon satellites. So what do we usually do with these carbon satellites? Of course, we do the inadequate experiment. And if you just take the inadequate experiment and take one of the phase cycles and flip it around, you're creating the anti-inadequate, and the anti-inadequate actually cleanly subtracts the carbon satellites out of our spectra. And with that, I end up with a carbon decoupled carbon spectrum, or I end up a spectrum where my neighborhood of the main signal is free of those carbon satellites, and I can see peaks which are really close to those fairly large peaks. And with that, I thank you very much for the attention, and I pass it back to Bob for the continuation. Thank you very much.
Clemens, this is Ken from Virginia Tech. I'm going to
okay, hi Ken. I'm
going to hammer you with the questions from the audience. You've had some really tough ones.
Okay.
And the first one is, where did you get that ancient hand crank from?
Oh,
But
you
that was
can
actually answered in the chat there, so you're free from
Okay.
that one. But that was interesting. I've never seen that before.
Hand crank centrifuges have multiple uses in NMR. I know people who put the thing upside down and spin the floaters and sinkers and all the solids in the sample into the cap, carefully tilt it back. It's a form of filtration also. If you Google hand crank centrifuge, you find about 100 places, of which will sell you one.
All right. So Hillary Jenkins has asked, when you're kind of working with these decoupling sequences, are you kind of doing this sort of trial and error, or are some that work better than others with polymers?
Okay, I will do that so you can see me. No, they pretty much work all there. It's really a question of, to some extent, it's the polymers. So on polyethylenes and polypropylenes, where you have very little chemical shift dispersion, the BiLife walls are okay because the BiLife part is limited in decoupling bandwidth. And so if you also have aromatics in there, they look lousily decoupled. You get really odd peak shapes, which are partially decoupled and partially not decoupled. So for tight chemical shift ranges, just the BiLife wall sequences are fine. But if you have to cover a large bandwidth, you're probably better off with the BiLife adiabatic sequences, which cover a wider bandwidth to work on.
Right. And
I can answer the question. Yes, I can provide the sequence. It's actually in the supplementary of the paper also.
All right. Bob, back to you.
Thank you, Ken, and thank you, Clemens, for that excellent talk. And that brings us to our fourth speaker, Alan Sentman from SGS Polymer Solutions. So Alan, if you could take the presentation away, please.
All right, certainly. Let's click the right button. Can you tell me if my screen is coming through all right?
Yes, I can see your screen. Thank you.
All right, excellent. So thank you. And I want to thank the organizers for having me out to talk a little bit about what I do and what I use NMR for. I'm a senior scientist at SGS Christiansburg. We are a contract testing laboratory. SGS is a large company that does a lot of certification and testing services. We are a predominantly polymer contract testing lab. So we are hired by companies and individuals who need to get some sort of analytical testing done. And so just a few things about this work. It has relatively short projects of relatively limited scope. So our standard timeline is 10 business days. And we are limited by what is necessary to answer the immediate question. So when sometimes we find something interesting that we'd love to do some additional analysis for, but are not able to do so. We're testing mostly polymers and small molecules, but really anything that our testing methods will be able to do, we will fit in. And so I've got polymer pellets there, and also a jar of peanut butter. I've done viscosity testing on 3 gallons of peanut butter for a cracker manufacturing company before. That one did not involve NMR, but really we see a lot of different things. Typically the sort of work we're doing, someone may have quality control or lot release testing. So they are regularly producing some sort of polymer product, and they either want to make sure every batch they make is good, or they want to hunt down an issue. That's not just the thing they're manufacturing. They can also be their incoming supplies. So sometimes the people who sell you your raw materials are a little cagey about what exactly it is. And so you may need some analysis to figure out what you're currently buying and find other sources. Failure analysis is a lot of the work we do, and that we'll use NMR for. And that's not just physical failure, something breaking. It can be discoloration. It can be unusual smells. There's a whole bunch of ways things can go wrong. Competitive product deformulation, just looking at what a competitor may have and what technology they put into it, and contamination analysis. That puts us in a little bit of a different environment than when I was doing university NMR and had control over my samples. The clients we deal with may not know much about what they're sending us. That might be because it's a competitor product. It might be that they're investigating process issues in their plant. They know what it should be, but they don't necessarily know what it is. And sometimes people just don't actually know a lot about what they're manufacturing. So as a result, we have some interesting cases. There have been cases where I'm expecting one type of material, and from the NMR, I see maybe a glycerin signal that looks like glycerin structurally. And I end up sort of furiously Googling before we put this in our report whether glycerin type materials are used with that plastic. And sometimes we've done some unfortunate things like sending Ken sample that is 30% iron oxide by weight, and everything survived, but we did not learn that until after we run the NMR. We are dealing with formulated products. That's very, very often, nearly any plastic that is a commercial plastic has additives, has stabilizers, has lubricants, has process aids, and has contaminants. Some products are cross-linked. Sometimes we know that going into it, and sometimes we don't. And low cross-linking density, you can easily still swell and run it. We often have to throw it at the magnet and see if it's going to work to find out. We do occasionally do magic angle spinning in solid state. And something I found surprising when I joined about 16 years ago, quantitation is pretty much always required. So for carbon NMR, we essentially never run 5mm standard carbon. We are always doing quantitative carbon. We do that in a 10mm probe with a relaxation agent to get the run times down. And generally about 2 hours of instrument time will give us a decent carbon spectrum with decent quantitation for most of what we're working with. So for the second half here, I'm going to talk about common cases and common experiments that we're doing. This isn't exhaustive. We see such a variety of projects that need more time to really delve into all of the interesting things. But what are we seeing daily? What are we using this for frequently? And so first, this is a bioabsorbable material. So this is a blend or copolymer of polylactic acid and polyglycolic acid. Those are used for things such as these. These are knee reconstruction screws. If you ever tear your ACL or MCL, they might drive one of these into the bone just above the torn ligament and then hang nylon sutures off of it and use it to stitch your knee together. These dissolve in time in the body into lactic acid and glycolic acid, and they're medical devices, and so they're very high levels of purity and such. So this is the spectrum of a similar material. Lactide or polylactide gives you big doublet here, big quartet here. The glycolide gives you a little bit more complicated spectrum down here. You can actually see some residual monomer in here as well. And you can get residual monomer, although we usually use GC there. And let me make sure I am not muted. I think it popped on and off.
You're okay, Alan.
I'm okay. Thank you so much. Now, there is an issue that you may not see with doing medical polymers. These are manufactured as medical devices, and so they come under the sway of the Food and Drug Administration. And the Food and Drug Administration has a set of rules for medical devices called Good Manufacturing Practices. We don't actually do a lot of production work on these sorts of materials. We do research and development work. If this data shows up as part of a FDA submission or an auditor who's reviewing the production process, the auditor will possibly come up the chain from our client to us and from us to Virginia Tech and ask to see all of the instrument logs. They want to be 100% certain that the instrument is working. This test has sufficient accuracy, precision, sensitivity, limits of detection, and limits of quantitation. And any change done to the instrument does not affect that. So if a newly trained student goes and retunes the probe, you would need to be able to prove that you still have adequate sensitivity. And so as a result, most of this work for GMP data is done by people who own and control their own instrument. But we do it for R&D. Let me refocus here. We do a lot of work identifying nylons. Lots of parts are made out of nylon. And an interesting quirk of nylons is the two most common types of nylon, nylon 6 and nylon 6,6. They have very different structures, but they have almost indistinguishable proton NMR spectra. For every CH2 on the nylon 6, there's a corresponding pair of CH2s on the nylon 6,6 that have really close shifts. And I actually have nylon 6 here on the left and nylon 6,6 on the right. And there are some subtle differences when you're looking closely. One of them, the arrows here are pointing at caprolactam, the monomer that is present usually in nylon 6 in small amounts. But for proton NMR, this is sort of asymmetrical information. If we know one of these is nylon 6 and one is nylon 6,6, you can reasonably well discriminate them. But people like to blend these two polymers together. And so we may be looking at what is the actual amount of each. And so carbon NMR works quite a bit better for nylons. By carbon NMR, and this is a blend of nylon 6 and 6,6, carbon NMR has just enough separation for you to be able to discriminate and identify which one you have, if it's one or the other. And also, you know, what the ratio is if it's a blend, and frequently it is. We do a lot of work at high temperature with polyolefins. So polyolefin materials, just common plastic. As an aside, one of the most complicated technologies you will encounter today is the shrink wrap film that is on top of a frozen food tray or a meat package. That ends up having 10 or 12 different layers of different materials, a lot of polyolefins in there of various types. So just some examples of what sort of olefin work we do. The top spectrum here, this is a blend of polypropylene with a little bit of polyethylene blended in. It's not a copolymer, because if it were a copolymer, you would see a few additional signals in the 45 to 35 range, and between 20 and 30, where you have an individual ethylene unit surrounded by polypropylene. That causes enough of a sequence break that you see a couple signals there that let you quantify them. The symmetry of that ends up being a little, trying to back that out into the weight ratio of monomers that went into it. You have to consider that sometimes identical groups came from different initial monomers. The lower spectrum here is a linear low density polyethylene. So you have a long sequence of straight ethylene, and then you may have occasional branches intentionally added. Different branch types give you different shifts here, and so you can actually back calculate that. And this is a linear low density polyethylene that has about 1 or 2% 1-butene copolymerized in. Polyesters are another common thing that we do a lot of testing with. Frequently, it's just polyethylene terephthalate, and that's real easy to discriminate. Sometimes they get clever and throw in different diols to modify the properties. I don't have a spectrum of it, but the other thing people can do is they can replace some of the terephthalic acid with isophthalic acid, which gives you a couple extra aromatic signals out there. So we'll sometimes, a project for this might be, both deformulation, what is my competitor using, might be, hey, I'm trying to compare A and B. They're behaving a little differently. They came from two different sources. What are the chemical differences between them? And then lastly, polyurethanes, it's not as cut and dry. There's a whole variety of ways people can modify their polyurethanes, and those are sometimes a little bit more of a challenge, less looking at reference spectra and more trying to actually go dig into what the materials are. And with that, I'm a bit over time, so I'd be happy to entertain any questions. And I would like to thank very much Ken and Gino at Virginia Tech. They work with us. We send sometimes difficult samples with insufficient information, and they do a lot of work making sure we can get good answers. So I'd be happy to entertain any questions, Ken.
Hey, well, thank you very much for coming. You've made up for all the hard work that I've done by giving this talk today. I will say we screen all of your samples with a magnet now before we them in the NMRs. But that was a fascinating talk. It's really interesting to see what becomes of the data that I send you. And I have to kind of ask, what's your like favorite, or what's your least favorite material? What's your nightmare scenario when it arrives in your lab?
The polyolefins are a bit rough, and it's so last week we got a set of 3 polypropylene samples, and it ended up being 2 polypropylene, 1 polyoxymethylene, and 1 polyester. And the client just had mistaken identities on it. So even with polyolefins, the high molecular weight ones, just trying to get them heated and dissolved in a way I can actually get a viable sample over to Ken is a lot of the issue there.
Well, I think this is interesting in the sense that a lot of polymer students here at Virginia Tech all have these dreams of boring academic work. And the fascinating work done in labs like yours with this variety of mystery samples to me sounds almost more interesting. Mm-hmm. But let me pass it. Go ahead if you want to comment on that.
No, it's just it is probably the single best thing about doing the contract lab work is we're always seeing something new. Get to learn a lot about new materials, and people send us unusual things all the time.
Let me pass it back to Bob for the final bit.
Okay, well, thanks, Ken. It looks like we have about 15 more minutes or so for the workshop. So we will now open the floor to anyone who has a question. If you do want to ask a question, and don't feel confident enough to write it, you can put that into or to say it, you can put it into the chat. Or if you wish, you can unmute yourself. Just tell us who you are, and then you can ask your question. I think maybe I can start a little bit with something that I think all of you had mentioned at times, talking about solubility issues and wanting to be able to get your sample in solution. I am a chemist by training, and so I tend to think of concentrations in moles per liter or something like that. How many moles of a sample is in my solution? But many of the engineers that I work with, they tend to think in terms of mass per unit of volume. And so they'll come to me and tell me, oh, yes, we've got a very concentrated solution. I've got so many milligrams of polymer in there. But because we need to know how many atoms are in there, the molecule is very big. And so just because you have a large mass in there, doesn't mean that you can see much with NMR. Maybe I can hand it over to one of the presenters to maybe comment further about that. Yeah. Clemens, you talked about the 10 millimeter probe, and Alan, you did as well. So how important is having a 10 millimeter probe in order to get so many more molecules into your spectrometer?
I'll take it first. So it's the 2 things. It's getting the molecules in the spectrometer and getting enough of the rare atoms in your molecule to see. And I think the idea is to maximize that. And that's where we've really seen that in the polymer world, our 10 millimeter cryoprobe has really become a favorite tool.
From our standpoint, I think the parameters were actually developed by likely Gino at Virginia Tech originally. That as the time we were developing this, they as a trade-off of we're trying not to pay too much time. We're trying not to pay for more instrument time than we have to get reasonable results. So that's certainly one way of getting a little bit more sensitivity.
There's one of the questions that just popped out in the chat. Out of curiosity, is it common to work largely with just 1D spectra? I guess all of the spectra we looked at today were one-dimensional. What role does two-dimensional NMR play in your polymer characterization?
Bob, I'm happy to take it sort of in the negative by saying all the questions we've been able to address with 1D NMR. And so for reasons of efficacy, we've never had the complexity to really go into 2D. So that's a negative answer. Maybe somebody else has a more sophisticated need and answer.
I think it will depend on the polymer. I mean, in the opening words to this workshop, it was mentioned that polymers, also lignins or products of trees and other materials, are polymers, and the entire lignin community is doing HSQCs and HMDCs all the time.
So yeah, I guess it just comes down to what question are you trying to answer, and in the examples we saw today, we generally knew what the molecule was, and quantifying was the really key thing, I guess. So.
It's certainly possible that I've run across questions that would be well suited for 2D, and I may not have the specific knowledge to recognize, oh, that the 2D would have immediately solved this. But the vast majority of what we're looking for, it's the same answer as Harald, that we're able to get what we need from 1D.
I'll throw a question in real quick to anyone who wants to answer it. One of the challenges I have here in the lab is convincing my polymer researchers to use carbon NMR instead of protein NMR to do their work, and convincing them of the advantage of the spectral dispersion that you're getting from there. I would love for you guys to help me with some of the Virginia Tech audience today and convince them of the advantages of carbon NMR over proton NMR for this kind of work.
One question that just showed up in the chat, are there any NMR experiments you can use to try to quantify amine content in a polymer? Now that's not anything that's come up here at McMaster, but has anybody had the issues with trying to quantify amines?
I've not run across NMR for that. Certainly, general analysis, we would go more for like a Keldol analysis for getting the nitrogen content, or there's a variety of titrations of increasing weirdness that you can use to get between primary, secondary, and tertiary amines.
You in principle could allow the amine, depends on the concentration of amines in the polymer, but you in principle could react the amines with something that would be NMR easily identifiable.
So make an amide or something like that, I guess.
Or just a protonation.
Oh, okay.
More quantitative, easy to do.
So another question for Clemens, and this was about the anti-inadequate sequence. So can you comment a little bit about the anti-inadequate?
Yeah, it's a pretty straightforward, easy sequence. It is sensitive to the coupling constant.
Right.
So it's more sensitive to the coupling constant than the inadequate as a selection, because you're really trying to suppress. So in my experience, I've seen about the chosen coupling constant plus minus 5 hertz, and then the satellite, then you have a residual satellite signal coming up. And of course, something for this community is going to enjoy that. We played around with possible names. So one option would have been to name it, take the inad out and call it the antiquate. But enough cute names out there, so we didn't do it. So other than that, again, if you have, let's say, if you work purely with aliphatic carbons, So polyethylene, polypropylene, it's going to work fine. If you already have oxygen attached to it, your coupling constants get quite a bit larger and you would see a residual signal still.
I guess if you're trying to suppress the satellites, you should be able to see them and measure the coupling constants and set your,
Right.
set your experiment appropriately.
Yes,
so
exactly.
Yeah.
And also, like many other sequences, you might have seen that there was a tiny residual signals on the satellites which have an AB system. So on higher order systems, it also does not suppress 100%.
Are there any, so if anybody would like to unmute and ask a question, feel free to do so.
I'll jump in with a comment. Ken asked a question and it's echoed in the chat. The carbon versus proton debate, it depends a lot on the polymer. We certainly do use proton when we can to get good info, but a lot of the polymers we work with, we really do need carbon. If you've ever seen the proton spectrum of like PVC or something, you definitely need carbon for that. And it certainly does help to have discrete separated signals for a lot of the work we do.
So quantitation is a big part of this topic area, I think. So I popped a question in the chat. Really, I was sort of wondering from our crowd, what's the de rigueur way to quantify these days, or is it just a combination of ways? So I was curious about signal injection, but one could compare that methodology to spiking with internal standards and that sort of thing. Are people doing signal injection or things other than spiking? Just curious. We in our lab tend to go, I guess I'll call it the old school way. If we're quantifying something, we'll put an internal standard in there, but I'm not sure that that's the most efficient way, and I'm not sure how well some of these other methods have been taken up and are now used routinely. I just have my own experiences to draw from.
Our experience is we use internal standard when we need total quantitation. A lot of the work we do, we can put an assumption that our sample is 100% polymer, so we can do basically a relative quantitation from the NMR alone without an internal standard. But we do internal standard for proper quantitation.
Fair enough. I wonder if I could segue to Krish's upcoming talk. Maybe there's a role for craft in here as well.
So if there are no other questions right now, then perhaps I'll hand it back to Dave Rice and he can wrap up today's meeting.
Okay, well, thank you, Bob. Are there any more questions? I noticed a couple coming up in the chat, and if people want to break in and ask their question directly.
I did see one related to diffusion, which I think is interesting for polymer talk. So Alexei was wondering about if anyone could comment on special probes like Doty probes or others, I guess, that are used for diffusion. So that's a general broad question. Maybe Clemens, I don't know.
I responded to Alexei privately, but I can give it to everybody. The diffusion is a useful tool for polymers, definitely, but you will hit a limit of the diffusion coefficient somewhere 10 to the minus 12 or something like that. After that, it gets difficult, and a lot of the polymers have also short T2s. Then that's another reason to get a probe with a higher gradient strength, where your typical 50 to 60 gas per centimeter are not going to be sufficient anymore, and you need more. And there are a number of places where you can get probes with higher gradient strengths, which go into the kilogauss per centimeter range, or which then allow you to do really viscous polymers, large polymers, and samples which have short T2s.
Have you ever come across sort of an upper limit on size, assuming spherical nature, I guess, of these molecules with respect to like those types of probes?
No.
Yeah.
Fair enough. Fair enough.
Yeah.
When it's solid, it's gone.
Right on.
There is always an upper limit, but there are a few very specialized labs which have even stronger gradients. So, and then at some point, fear is going to kick in that the gradient is going to affect your magnet. So when you pulse it that hard.
So I'll jump in. Are there more questions? And if there aren't, I would like to thank Bob and all of our panelists for really a great set of talks here. And I would also remind everyone again about our upcoming Ivan ENC meeting. And I hope that you will be there and take it as the relaxed meeting it is, in addition to the good talks.
And Dave, if I could,
oh, great.
If I could jump in on that, I apologize for being tardy for today's meeting. I was out getting Pfizer dose number 2. In fact, Bob Berno wanted me to live stream getting the shot. And well, Bob, we'll save that till next pandemic, and we'll see what happens. But my belated thank yous and welcomes and so on and so forth. We do appreciate everyone joining us today. And as Dave was mentioning, of course, the big upcoming news is Sunday, March 28th. I know it's a Sunday, but please do your best. Sunday, March 28th, pre-ENC Ivan meeting. And we're hoping for a really good turnout. The official start time is 10 a.m. And again, I know Sunday, but see what you can do. However, the real fun starts at 9:45. These are all Eastern time. And Dave, Dan, and Lima are all going to be physically on the shores of Asilomar Beach, surfboard in hand, by the way. And I will promise a very, very fun-filled day. We're going to have a great lineup of speakers, great prizes. I can promise you that. We certainly didn't have to shell out a fortune for a live meeting this year, so we're going to have some great prizes, a lot of fun, and I hope everyone will join us again. I know it's Sunday, but I promise a good time for all, and it's going to be a fun day. And but anyways, thank you everyone for joining us in today's meeting. And Dave, I'll turn it back to you to close out.
Okay, great. Well, thanks, John. And I'm looking forward to the meeting and looking forward to getting up to being on Asilomar Beach at 6:45 Pacific time, which is actually slightly before sunrise. So everyone will see sunrise at Asilomar Beach. So come and visit us to see how we do.
Dave, I just wanted to mention, I neglected that we have sent out a number of notices already. And for those that have not received them, you can certainly sign up for the Zoom meeting on the Ivan website, Ivan MR, IVANMR.com, and give you the agenda and so on. But anyways, back to you, Dave, and we'll close up shop.
Okay, great. Okay, thank you, John. Okay, so with that, I'll declare the meeting closed. And thank you everyone for coming.